pick up one of them. Derek and Vince. Thank you. You can sit here also if you want, I mean, if that's too congested.
Okay.
I don't know if it's your preference, but.
I didn't see it.
All right, let's get started. What I want to do today is Helmholtz equation in cylindrical coordinates. So what we did last time was this is what we want to do today. So basically, Helmholtz equation is nothing but time-independent Schrodinger equation. Okay, so that's what it is. Mathematicians call it as a Helmholtz equation. So this is something you will come across all the time. All right. So I'm going to write the Helmholtz equation. I mean, and I'll write the del square psi plus k square psi equal to 0, where in the Cartesian coordinate psi is function x, y, z. Now it's going to be a function of rho phi z. Okay, I mean, I'm going to talk about that. Okay. So supposing we'll come across this like heat diffusion equation kind of a thing, but a steady state diffusion equation, let us say, it will be looking somewhat like that, right? I mean, in cylindrical, let's say you have cylindrical plate or something like that, you may want to use a cylindrical coordinate system. So what I want to talk about is supposing a point in our position vector point P. We know how to write that in Cartesian coordinates, right? The displacement vector R. That we have already learned. I mean, you already know how to write that. So it will be something of this nature that you know, right? So many times I'm just saying, like, you may have a problem where you may have a cylindrical geometry, and maybe you have held the temperature here at some constant, and you want to find how the temperature is distributed along the cylindrical rod, as supposing this infinite rod or something like that, as an example. Okay, I mean, you want to know in steady state how the temperature looks like, the temperature distribution. That's in that case you would automatically use cylindrical coordinate system, right? Because of the geometry of your sample in this case. So what we have to know here is how to write del square in cylindrical coordinates. That's what we have to learn. So I want to tell you where things are coming. I'm going to show this to you right from first principles in some sense. So this is something you know how to do it. Now what is x? X, based, if I use this coordinate system, cylindrical coordinate, it's nothing but, rho is nothing but projection of the r vector in the xy plane, and this distance is rho, right? And phi is this, and z is something, supposing my rod was like that, right? I mean, something of that nature, then you would use rho phi z kind of a system, right? So what is x? X is nothing but, in this cylindrical coordinates, is rho cosine phi I plus rho sine phi j plus zk, right? So that is the definition of rho if you use the other coordinate system. All right, so I just put it just to say what is rho and all that. So that's just the dimension of this, cylindrical rod or plate, whatever it is, cylindrical solid, let's say. Okay, so this is my traditional ijk are the Cartesian unit vectors in traditional Cartesian coordinate system. Now, if I just take the derivative of this, a partial r, in fact I should do because r is function of rho, phi, and z. If I do partial r with respect to phi, what do I get? I get cosine phi I plus sine phi j, right? And I'm going to write, I can write partial of r with respect to phi. If I did that, it will be minus rho sine phi I plus rho cosine phi j. And if I did the last one, partial of r with respect to z, I would get simply k. So I get three, what are these? I mean, can I call this partial r with rho as a vector? It's got direction, magnitude, so I can call some vector, right? So let me call this as E rho vector, okay? And let me call this as E phi vector. And let me call this last one as Ez vector. Now, what is the magnitude of this vector E rho? 1. What is the magnitude of vector E phi? Rho, right? And what's the magnitude of Ez? 1, okay? So this vector E phi has the magnitude rho, right? The other vectors, let me go, E rho has magnitude 1 and Ez has magnitude 1. Okay, that's first thing we observe. We generated, starting with some position vector, we generated 3 other vectors, okay? And what is this property of E rho, E phi, and Ez? Can you tell me one more property of this? We know these two have unit magnitude, okay? What else can we do? What else can you put? Just I'm putting some equation. Can you observe anything else on this? If I dotted E rho with E phi, what happens? Dot product of E rho with E phi. 0, right? And dot product E phi with Ez? Is also I dot k is 0, j dot k is also 0, right? They are orthogonal. So what we have done is we have generated 3 orthogonal vectors, E rho, E phi, and Ez, first thing. Now, supposing I also, if I divide this by 1 over rho dr, or then I get what? I mean, that's again is orthogonal, but I can make, I'm generating 3 unit vectors now, okay, which are mutually orthogonal. So from ijk coordinate system, we have gone to E rho, E phi system, and those are the unit vectors in the rho, phi, and z direction. Okay, is this clear? Is this point? I mean, maybe I should have written everything in one line, then you could have seen it clearly. I started. So, okay, so what we have is the following. Okay, let me first, so we have 3 vectors now. E rho is exactly equal to unit vector, okay? Ez is also exactly equal to Ez unit vector. Okay, if I wanted to create E phi unit vector, what do I have to do?
1 by rho.
I have to do E phi divided by rho is E unit vector. So I have generated 3 unit vectors which are orthogonal to each other. It doesn't matter, this is a constant, rho is a, so we have basically E rho dotted with E phi is 0, E rho dotted with Ez is 0, and E phi dotted with Ez is 0. So from ijk, which are mutually orthogonal system, I've gone to another mutually orthogonal system from E rho, E phi, and Ez. That's all we have done. Now what is the direction of these vectors now here? What is the direction of E rho unit vector? Let us say, this is my I direction, right? And this is my j direction. Okay, let's start with the simplest one. This is simple, right? First one is same as this, which is Ez hat. Okay. I is like this, j is like this, right? At this point. Sort of I plus j direction, the other one will be like minus I plus j direction, okay? So minus I would be what? We have to also, the way it is it will increase the angle. So E phi, one is like this, right? And the other one would be like that. And which is which? Minus I is here, right?
E phi points to the top right.
Which one?
To the top right, like in the negative I direction.
Yeah.
This one?
Yes.
It is
E phi.
E phi. So it should be in the direction where it's increasing the angle phi basically, and that one increases rho basically, the length of the rho vector. So from ijk we have unit vector. We have created under triple vector rho phi z. Okay, so that is sort of now. All right. So I want to. So if I have to in this new system, coordinate system rho phi z cylindrical coordinate system, if I have to write a displacement vector, how will I write it? That's total derivative dr. R is a function of phi, rho, phi, and z.
So we will plug this and put dot product with unit vectors.
I want to give you, I want you to say in terms of,
This.
I can always write it like this,
Yeah,
right?
Dot.
Partial of r with respect to phi, d phi, partial of r with respect to dz time dz, right? The total displacement vector, it's r is function of phi z, so I can write it like this. And I have an expression for all these things, right? Partial of r with respect to rho is that, which I can write as unit vector in the direction, right, d rho. I can write that. dr with respect to phi, it's e phi full vector, and that full vector is nothing but rho times unit vector. Okay, so here I have rho times e phi unit vector d phi, and this one is right. How would I have written this in Cartesian coordinate system, dr vector? What's the difference I want to do? If I in the Cartesian coordinate system, what is the analog of that? I, j, k are the unit vectors in the Cartesian coordinates. So if I wanted to write dr, a displacement vector, what would I have written it as?
Partial derivative of r with respect to x dx plus partial derivative of r with respect to y dy and so on.
Yeah, but that is equivalent to all these things. Now you know how to write that also, right? It's I unit vector dx. I just want to see that analogy, okay? So I'm going to put this out so that you understand. I mean, these are the unit vectors. So here it has become rho d phi times unit vector in the right. So that's the important thing to notice. So when we go from, I just want to also generalize this because we call it rho phi z as independent variable. When you write a generalized coordinate system, whether it's spherical coordinate system or anything, I'm going to generalize this as u1, u2, u3. Okay, where u could be in the spherical coordinate system are theta and phi, right? I mean, now the scale factors that we define are nothing but in going into curvilinear coordinates, you have these scale factors h1, h2, and h3. They are nothing but magnitude of these e rho, e phi, and ez. Okay, so h1 magnitude of this is nothing but magnitude of this guy, the first independent coordinate, whatever you are doing it, which is equal to 1 in cylindrical coordinate system. h2 is nothing but partial of r with respect to phi. The magnitude of that is rho, it's not 1, right? And h3 is partial of r with respect to z, which is equal to 1. So these are called as scale factors. So in Cartesian coordinates, the scale factors were exactly equal to 1 in all dx, dy, dz, whereas here the scale factor is rho d phi, right? I mean, we have scale factor is rho basically, h2. So you can see the analogy. If you forget it, you just have to, this you remember, right? R is x, I, y, j, z, k. So dr has to be like this. So I becomes e rho in this right? J becomes this is e phi, I should have written, right? E phi. So when phi becomes phi plus delta phi, the amount of displacement dr is not d phi, it is rho times d phi. Okay, that's what it is. The displacement vector, when phi becomes phi plus delta phi, it changes by this amount. Okay, so that is the difference here. Okay, so these are scale factors, and I want to generalize this in terms of u1, u2, u3, and and write a general expression for gradient phi and then del square phi. Basically, I want to, the whole idea of this exercise is just to see how to write del square in this coordinate system, okay? And I also want you to have an appreciation of where these h1, h2, h3 and all, when we write in that expression, what is the meaning of that? It's really nothing but the magnitude of the displacement vector with respect to whatever the independent coordinates is. Like these will change in spherical coordinates. You have to, if you want, you can derive h1, h2, h3 right from scratch like this for spherical coordinate system. Okay, so I think one of them is r sine theta, one is r, and one is 1 or something like that. You can get that explicitly. So you don't have to worry about it once you know where they come from. I mean, the definition of h1, h2, h3. All right. Okay, so I want to generalize this now. So here we still consider orthogonal coordinate system, right? But it not necessarily be orthogonal coordinate system, and you still can write all this stuff. All right, so I mean, I just, when I say not necessarily orthogonal coordinate system, it's something, they don't have to be like that, okay? So let me call it U1, U2, U3, I mean, very general, and these, you can put a tangent to these curve and they will represent the direction of U3 hat and U2 hat and all that stuff. But what I want to say is, let us write in this coordinate system, instead of, I want to generalize, right? Rho is E1, just anything, I mean, at this point, will then be 1 over H1, the scale factor, which in our case, where is the E1 factor? Okay. So this is E phi, right? And what we said was, this has got magnitude rho, right? Magnitude of E phi was rho, which is really H2 for you, right? I mean, if I want to write it generally. And we have unit vector is nothing but 1 over rho times E phi. So if I want to write it generally, this I'm going to call it as E2 unit vector in the direction 2 is nothing but 1 over H2, because this is, I'm going to write it generally like that, right? And this is the definition of E2, E1 and E2, they are fine. I mean, we can put it, if it's not orthogonal, let me just put it 1 over H1. Okay, so this is the definition of E1 unit vector, which is 1 over H1 E1 vector, okay, in a generalized coordinate system, and E2 would be 1 over H2, which you can understand from here, right? Partial R, just some changing the notation, that's all it is, okay? So for cylindrical coordinates, U1 was rho, this is phi, and this is z, and spherical will be r theta phi. Okay, and then you can get the scale factors also, corresponding scale factors and all that. Okay. All right. So so this is because I want to write it generally, right? So let's try, because my goal is to write del square phi in the Helmholtz equation, how to write it. So we know it is divergence of gradient of phi. That is what is the definition of del square phi. So I want to write del phi in this, in terms of u1, u2, u3, and h1, h2, h3. Let's see what happens there. Okay. So the way to do this is as follows. I know how to write d of r in any coordinate system. So can I write, again, all of them go like this, total change in phi, I can write as gradient of phi dotted with the displacement vector, right? It's the same thing like dr, how do you write is a partial with. So similar kind of a, this is partial, right, in some sense, for phi with whatever the independent coordinate system are. Now what is a dr vector? How do I write the dr vector? In terms of u1, u2, and u3. So you know this, how to write it. And we also had wrote in the cylindrical, what you wrote, I want to write it generally, right? And this was E row vector, D row vector, and this was E phi vector, D phi. This is EZ, DZ, which I have to write in terms of unit vectors, right? I mean, which is this. E phi was what? E phi is rho D phi. The rho D phi. And the last one is. So this is my displacement vector. This is my displacement vector in cylindrical coordinate r phi z. Now I want to write it in terms of u1, u2 in a very general way, right? Because that way we'll have a very general expression, and all I have to know is what is h1, h2, h3, u1, u2, u3. I'll have to plug the numbers. That's it. Right? So where those formula come from? So what is dr vector? This was E1, right? What is okay? So this came from what? Dr over d rho. In a general thing, it need not be. We have to have a scale factor, right? So so I should have it as what? Can I write it as h1 E1 unit like this, first term. Because I'm writing it generally at this point and for any coordinate system, right? They're all coming from H1 happened to be one for cylindrical coordinates and one for cylindrical. Need not necessarily be, okay? So I'm going to write the displacement vector like that. All right. Of course, this is nothing but, that is nothing but E vector. In some sense, if you forget it's this is a vector, that is a This is E1 vector, this is E2 vector, and this is E3 vector, not unit, right? That times that you can also write it that way. Okay. So I'm trying to write this, right? So I can write it like this: H1, E1, DU1, H2, E2 hat, DU2 plus H3, E3 hat, DU3. Okay, so I'll just substitute for dr vector here. And I have to somehow get an expression for gradient phi. What can I do for del phi? What are the independent coordinate system here? What I'm trying to hear. There we had rho phi z, right? I'm writing the whole thing for a generalized coordinate system. Okay, it could be r theta phi, whatever, right? I mean, so the total change then can, in potential, let us say, because gradient is normally comes in acts on a scalar, right? What should I write d phi as if u1, u2, u3 are the independent vectors? Think of that as d phi was Cartesian coordinate, or how will you write it in terms of total change in potential? If phi is a function of x, y, z, how will you write it? It's all the same kind of a argument, right? How we wrote dr, or only thing is the independent variables u1, u2, u3 for you. Just take a guess.
So you want Cartesian coordinates?
No, I want it in u1, u2, u3, but because I thought you may be more familiar with Cartesian, think about it and then translate that to u1, u2, u3. A function, this is a function of many variables, right? I mean, three variables, I mean, in this case. And what I have is total derivative there. And how do we connect it to? I mean, we wrote it here, right? I mean, where we did somewhere. Yeah, there on the top. Yeah, dr vector. That's total left hand side, right? If it's a function, r is a function of rho phi z, then what is dr? What we have written. It's a similar argument you have to use. Except r rho is u1, the other one is u2 and u3.
Partial derivatives in respect to r with
No, that's
u1,
your function
u2,
is
and u3?
Fine, yeah. So it's here scalar, but it's all you have to do is partial of phi with respect to u1, right? Plus d1, right? The total derivative, partial of phi with respect to u2. That is total change, right? Partial of phi with respect to u3, du3. So my left hand side is this, which is equal to gradient of phi dotted with h1 e1 hat, h2 e2 hat du2 plus h3 e3 hat du3. Okay. This is clear. What I did was just replace the total change in phi by this, which I can do because it's a function of, that's because phi is a function of u1, u2 and u3, right? And this is, so, and I use this property and I know how to write dr. Dr is a vector in terms of the generalized coordinate u1, u2, u3. I can write it like this. Now when you do this, can you see how do I extract? We have du1 here, du1 here, du2 here. So if I compare those terms, what do I get? Relays all these things. Can we say something comparing right hand side and left hand side? What can we infer from there? Can I say partial of phi with respect to u1 must be same as
H1.
h1 times gradient of phi? That's a vector, right? And this dotted with E1 vector. Okay? Or gradient of phi with respect to E1 vector is nothing but 1 over H1 partial phi with respect to U1. Okay? Similarly, compare du terms on both sides. Okay? Then you have partial of phi with respect to u2 is nothing but h2, partial of phi with respect to u2 is h2 h2 times a gradient of phi times e2 vector, and the third term will be of course partial of phi with respect to u3 is okay. It says gradient of phi with respect to dotted e3 is nothing but 1 over h3 partial phi u3, and similarly you have gradient of phi with respect to e2 is nothing but 1 over h2 partial of phi with respect to u2. Okay, so what does that tell me? What is this? Partial, partial phi with E1, what does it suggest?
Just the dot product with the
Hmm?
dr vectors dot.
So that's like the first component
Yeah,
of the
that's
gradient vector, right? I mean, if you have like that dr with I, if I do, others will cancel, you get dx, right? So it's the x component there. So we can say, oh, that means is the first component of gradient phi. I'm not going to rho phi, but I'm just saying this is the second component of gradient of phi in u1, u2, 3 coordinates, and this is the third component of gradient phi. So I can construct gradient of phi from there, right? I mean, so that's how you get the definition of gradient of phi. Okay, so we have it as 1 over h1. That's the magnitude, right? Times e1 vector plus 1 over h2 partial phi with respect to u2 vector plus 1 over h3 partial phi with respect to u3 e3 vector unit vector. All right, so this is just to say we just started from scratch. What is h1, h2, h3, and we constructed a gradient of phi. Okay, so once we have that, we can construct del square phi definition that you will see all the time. You will not, you'll be using it automatically afterwards. But I just wanted you to know where these things come from. So similarly, so as I said, del square phi is nothing but divergence of gradient of phi, right? Is del square phi. So I need to, what I have done is getting del phi, gradient of phi in the curvilinear coordinates. We also have to know how to get divergence of a vector, where f is some vector, in curvilinear coordinates. There's a formula for it, and I'm not going to derive that, but you can look at your book, but this is the general formula for any system, and from there f1 is the first component of the vector f. F3. Okay, so H1, they have the same, these are scale factors of the displacement vector with respect to whatever the coordinate system is, the magnitude of that, okay? For cylindrical coordinate, this is 1, that's 1, this is rho, okay? I mean, so if I put f equal to gradient of phi, that is my vector, then I can get del square phi, right? So my goal is to somehow get this. So I have 1 over h1, h2, h3 partial with respect to u1, the first coordinate system, the first independent coordinate, h2, h3, and this is the first component of gradient of phi, so which is nothing but, I have h1 in the denominator, now partial of phi with respect to u1 plus partial with respect to u2 of h1, h3, f2 is this guy, partial of phi with respect to u2 plus partial with respect to u3 of h1, h2, f3 is h3 is partial of phi with respect to u3. Okay. Okay, so cylindrical coordinates, if you have to get if you want to get del square, we'll take h1, let me first write u1. u1 is rho, u2 is phi, u3 is z, and h1 is 1, h2 is rho, h3 is 1. Okay, so you have to use all these things to get del square phi in cylindrical coordinates. The problem, homework problem that I've given is in spherical coordinates, so let me just write down for that, so that so u1 is r, u2 is theta, U3 is phi. Okay, that's a polar angle actually. And H1 is 1, H2 is R, H3 is R sine theta. Okay. If you want, add this also to your homework, derive H1, H2, H3 for spherical coordinates. All you have to do is, partial R with respect to, these three different. So you know where they come from. They're nothing but the magnitude of dr with respect to dr, and dr with respect to theta, dr with respect to phi. The magnitude of that displacement vector with respect to that, right? I mean, that's how we get it. These are scale factors. The definition, these are very general definition, right? Partial r with respect to u1, partial r with respect to u2, partial r with respect to u3. So you have to get these things explicitly. We derived it for cylindrical. If you want, derive that and then start the Helmholtz equation. Okay, let's start with the Helmholtz differential equation now. Back to this, what we wanted to do. So let me have this. So this is outside all of them. So remember, you have to take it in for each one of the terms. All right. Sort of it goes in a cyclic fashion. For the first component is, it's H2, H2, in the denominator you have H1. So the second one, H2 is in the denominator, the others are there. So you can, that's how it goes. So it's not very difficult to remember this form. Okay, so our goal, of course, is to solve this problem. Del square phi plus k square phi equal to 0. Okay. Helmholtz equation in cylindrical coordinates. Right. So we now have del square in expression. So what is 1 over h1, h2, h3? 1 over rho, right? Partial with respect to rho, that's my first coordinate. H2 is in the numerator, rho is in the numerator, so that's fine. Partial of phi with respect to rho plus partial with respect to phi, the azimuthal angle. H1, H3, rho is now in the denominator, partial phi with respect, this is my potential and this is my independent variable. Maybe I should change it to psi or something so that, let's see, let me call it psi so that. Okay. Okay, that's my second one. and partial with respect to z, which is the independent coordinate. Rho is in the numerator, partial of psi with respect to z equal to 0. Alright. Now I'm going to take rho inside because otherwise I'll forget it. It has to be there. So when I take it inside, we have rho here. This one doesn't depend on that, so I can pull this rho out, right? It's 1 over rho square. And this one doesn't depend, so the rho and the rho denominator will cancel. Okay? All I did was the rho which was common, this one, I pulled it inside, it's you know, factoring all the terms, so I have it, otherwise we'll miss it. So I can write this as partial, second partial of psi with respect to phi, and this now I can write this second partial of psi with respect to z. Okay, this is all these del square. Don't forget my k square term. I'll be in trouble otherwise. Okay, so this whole thing is del square. Okay, and plus k square psi. All right. So this is a partial differential equation in rho, phi, and z. And I need to convert that into an ordinary differential equation. What do we do?
Separation of variables.
So I should write what? The solution that we are seeking should be product of 3 functions. Let me call the first function p. It's a function of rho only. Second function phi. The big is a function. This is the independent variables. Z is the function. Small z is the independent variable. I can write like that, right? All right, if I did this, what do I get? I'm just going up now. So this is a function of rho only, so I can pull phi z function out, right? I mean, let me write down here maybe. So phi z can be out, and this will become, I have a rho here, cannot take it out. Let me, d over d rho, rho dp over d rho. So this has become full differential now from partial, right? I mean, I substitute for psi, that, but I can pull phi and z out. Okay, so just check my algebra. 1 over rho square. Now here it is p and z. So the big function p and z can be out. And this one will be total derivative of the function phi with respect to this independent variable phi. And the last one will be what? P phi O times d square z plus k square p phi z equal to 0. Right, this phi is a function of all that, so I just put that. So we have converted using this. So this has become now from a PDE to second order differential equation. It's become an ordinary differential equation in rho, phi, and z. Right? Now what do we do next? These are functions, right? I want one second derivative to one side.
Divide by rho phi z.
P phi z.
P phi z.
Yes, sorry, I should, yeah, rho is an independent variable. This is, P is a function of rho, okay? So this is the function. I'll just put it up so that you understand what that is. Divide by P phi z, yeah. Okay, so this, then I will have here 1 over P, 1 over rho, function is in the denominator here, in this rho, dP, d rho, I have 1 over rho square, hope I don't need this, okay, remove that. Okay, so 1 over rho square, 1 over phi, d square phi, d phi square, 1 over z, right? So it's all not total differential. Okay, what's the next step, which looks that I can pull it to the right hand side? Can I pull this, because this is now function of z only? So let us pull this to the right hand side. Okay. If I did that, I can remove this. I'll delete it from there. I can write it as minus 1 over z, d square z, dz square. Get rid of that. Okay. So what can we say about this equality condition?
Both sides must be equal to a constant.
Right. So this is a function of rho and phi, and the only way we can satisfy is this guy is a constant. I mean, of course, both sides have to be constant, and now we have to decide all right, supposing I again take this case of infinite cylinder, and let's say we are heating only at the bottom. What do you want? What do you think in that case? Supposing that was a problem. I mean, again, I cannot decide. But so that was a problem. But z equal to infinity, this is the solution. Z would be your temperature in this case, right? What is the type you would like to have? So I want to decide the sign of z as a function of z. What kind of function form? Because you can guess the solution at this point, because it's almost like a fairly simple second order differential equation. If I chose the positive sign, what happens? What happens to that kind of a differential equation at z equal to infinity?
Second derivative.
Second derivative of z with respect to z is then negative L square, right? Because, so what is the solution of such an equation? Second derivative of z with respect to z is minus L square z. What is that differential equation? If it chose the positive sign, the upper sign. If I chose this, the positive sign, because of this negative sign, this is my equation, right? Minus L square Z.
Is it exponential?
What exponential I want you to tell me correctly the exponential. Does it satisfy that equation if you put exponential of LZ as a solution? You take the derivative 2 times, will it satisfy?
Exponential of IZ.
Yeah.
Yes, minus ILZ. It's an oscillating solution. But is this a solution that I want if I want the temperature at infinity to be oscillating? You don't want. You want that to decay.
Yeah.
So in this case, I don't want a harmonic oscillator kind of a solution. This is a typical harmonic oscillator kind of a solution, right? I mean, Hooke's law kind of a thing. I mean, that is not what I want. So in this case, I don't want this sign, but I want this sign. Okay? So then I'm able to choose, I mean, such an equation, I mean, if it was this, I could have 2 possibilities, right? Both of them will actually satisfy. Even, but you know, the problem can be such, I can choose a boundary condition such that this goes, and I'll take that as my desirable solution for that kind of problem. If you have a solid, I mean cylindrical solid, and want your temperature decay to infinity, I want this solution. So it is this this is a sign we are trying to determine, plus or minus. So I want this equation to be like that, okay? Okay, so we have decided the constant, it is going to be negative L square, not positive L square. Then this is negative L square, we can start substituting this, right? And I can bring it to this side, so it becomes k squared plus L square equal to 0. Okay, so yeah, so I will not take, both will satisfy it, right? It's a second order differential equation, will have 2 solutions. It's like any, you know, a second, so it'll have, but this solution is not physically meaningful for a certain problem. Mathematically, both are possible. We'll say, we'll throw this solution because it doesn't satisfy whatever you know, your boundary condition or the physical problem. Okay, okay, now we have that. Now can we take, but we have got a rho square too here. Okay, so what do we do next? Because I want that only that term to go to this that side. So can we multiply by rho square so that I can get rid of this from here? Okay, so multiply by rho square. So that this term has got only that, right? So we can then, what I get is 1 over p, the function is there, rho is now in the numerator because I multiplied by rho square, rho dp over d rho, this is my function, plus, now I have only a nice equation only in rho, because here rho and phi are mixed, I want to get rid of it. And I have k square plus L square times rho square equal to 0. Okay? So since this has been multiplied, I have to multiply by that. Okay? So now the next step, as usual, will be this. I need to bring this to the other side, and we will use the same kind of argument. Give this. So I'll say 1 over p rho k square plus L square times rho square is negative 1 over 5 d square phi, big phi, with the small, this big phi is function okay. So again, I want to keep something like this in mind. Let us say, these surfaces, these two curved surfaces, here it is on the bottom surface is temperature 0, curved surface is something here, and it is 0, let us say. I just put a cold bath on the side, ice or something like that, let's say on the side only. So what kind of a solution should I want? How can I make, it's a finite diameter rod or cylindrical rod. It's a constant. Should I take plus or minus? The separation constant sign, what should I choose? So we have seen if you have question is, should I choose that or this? In one case, in which case I have a sinusoid solution? First one, second one. M is any integer. Supposing I have something like a sine m phi and cosine b cosine m phi, right? The other one is exponential of m phi. It's very hard for me to make it go to 0, even m equal to 0, right? And the other one I can make it 0. So I will choose this solution in this case. D square phi over d phi square is minus m square phi, or negative of that is equal to plus m square. This is plus m square because there's a negative sign here too. Okay, so m square is under constant, because in such a case the solution could be phi as a function of phi. I could write it like this: a sine m phi plus b cosine of m phi. And of course the other one, z as a function of, I will have both of them, but I'll get rid of one of them, right? Mathematically, of course, both are possible. If you want, you can't call it A, B, I used C, D, something. The M, the M. All right. So we have that. Let me bring this to this side. Minus m square equal to 0. I got this function sitting at the bottom. You don't want to write a differential equation with the functions, you want to, so multiply by p, okay? This looks like a constant, something I can replace by something n, okay? So what I have is the following differential equation, which is rho right? All right, this is the equation you get, and this is the second order differential equation in P, and this is called as Bessel differential equation. Okay, the independent variable here is rho. So what we have seen is the following: the Helmholtz equation. In cylindrical coordinates, right? Psi is of course function of what? Rho, phi, z. It is split into three ordinary differential equations. One of them is this. The one in phi became this. Let's call it d square phi over d phi square. We want to take it, let's say, minus sign. And the last one in z is also a simple one, decaying solution. So I want to write it as plus L square z. So this is what has happened to our partial differential equation. These two I'm able to guess the solution. This one we have to learn techniques. This is where the next couple of chapters will be how to solve somewhat more complex differential equation through learning techniques to solve them rather than guessing the solution. Okay, we were guessing the solution because I can say, okay, if I take 2 times derivative, can I get the right hand side? When can I get the? Can I put the exponential? Real constant z or exponential imaginary, ILZ, and we are guessing whether it's sinusoidal or decaying solution, mostly exploding or exponentially decaying solution. Those are the possibilities, right? Okay, so so I'm going to write this. I will. So if you see any map book, this is how it will be, the canonical form of it will be written like this. Y is a function of x, right? X. The second term is first derivative, x squared minus mu squared if you want. Can be n squared if it's real, nu can be real integer or real. That plays a role, I'll tell in a minute. So something like this, it's a second order differential equation, it will have 2 solutions. And so the solution of this is Bessel differential equation. It's normally written by this symbol, J nu x actually, where x is whatever is here, okay? Here we have n square rho square. So it will be j nu x, 2 solutions as I said. One of them will be j nu, the other independent solution is j minus nu x. These will be the 2 solutions of such a differential equation, and we will, the whole idea of special function, what is j nu x, right? I mean, that's what we will try to understand. The properties of this Bessel function is what we will try to understand in the next couple of, yeah. I'll write down the form of it. It's an infinite series basically, and it has this form. So it'll be sort of an oscillating function. Okay, it's not sinusoidal or anything, but it'll be some kind of a oscillating function. Like if you have a cylindrical drum, you know, you have oscillations, right? I mean, one of the solution will be Bessel function. Oscillation is really coming from that part of the, if you have cylindrical drum and vibration, because that is your wave equation, right? I mean, and so one of the solution would look like something like that. Now what is gamma? This is also a special function. Gamma, if nu is an integer, this is nothing but, this is nu plus n factorial, same as that. The advantage of gamma function is you can write for, you know, you can extend, it doesn't have to be an integer, okay, nu could be half or something like that, okay, I mean, so it is really, gamma function is really nothing but a different way of writing factorials, okay, so anything nu plus n, we'll do all these things, okay, so this is gamma function. So it's pretty, you know, you can see that this is not a simple solution, this differential equation solution is not simple. So we have to learn the properties of what is this Bessel function, because it's going to come all the time, right? I mean, so this is Bessel function, and so it is an oscillating solution. I mean, it's oscillating. That's all you have to remember. It's something oscillating. You can, you know, do the summation computer up to certain terms and look at it, where it, what happens to it. In some sense, that's what you do. Yeah, so what was it? Yeah. Right, so all of them are, you know, second order differential equation. It will have two solutions, but depending on the boundary condition, we are eliminating one of them. Here, in some cases, we'll say, oh, I want to eliminate this because it becomes infinite at x equal to 0 or something like that. We can eliminate one of them. What is the physical solution, right? I mean, so all of them will have ELC and E minus LZ as mathematically both are possible, okay? I mean, and this is sine and cosine, both are, there are two solutions, and here it's J nu. So, okay, now what I want to say is, this is our actual differential equation. So how will I write the solution in this case? Identify, this is, if this is a, you know, this is a differential equation, the solution is written like that. So in this case, what should I write? My nu is like m, right? And this will be the solution of that, because, you know, it is, the variables are different, right? G, M, and rho. So what we'll do is, we'll start, you know, power series method, and go through the differential equation, and all that will depend on how these functions behave and all that. We will talk about it and how we develop different types of series solution, because it should not blow up. I mean, whatever series solution that we develop has to converge, right? I mean, so that's what we'll do. I mean, all I'm trying to say is, you have to do wave equation, you're automatically going to get some second order differential equation. And the homework problem is, you have to solve this in r theta phi, spherical coordinates, right? And I want you to develop the equation r, theta, and phi. What does it, you know, what second order differential equation it develops into? So you have to use the separation of variables method, and go through this so that you are comfortable with, you know, with the method itself, separation of variables method. Okay, so that is the goal of it. So you go through the technique step by steps. You know, I mean, you have the solution as product of three functions of r, theta, phi, and you know, do the, you know, take a term which is only a function of r, term function of theta and phi, and separate it out and see what three differential equations you will end up with. So there, R will be a spherical Bessel differential equation, slightly different, but you will recognize some other term. Theta will become complicated, associated Legendre polynomial, and the one in Z, phi will be simple like this, okay? I mean, like a simple harmonic oscillator or exponentially decaying or exploding solution kind of a thing. Okay, so that's what, so do that homework, and then we'll start with the main part of this, which is second order differential equations. Now start learning all the techniques, how to solve them, okay? Good. Everybody got the homework? Yeah. So a week from today is the deadline, and so far this is motivation why we have to do second order differential equation, because if you have